Okay, so here we are. We got cut off a little bit from the previous video. Let's finish up this one, all right? So we're on number 17G, baking soda. What do you think? Baking soda, is it a element, compound, or mixture?
That's the chemical formula there, right?
Yeah, okay, so baking soda has a chemical formula. So it is a compound, right?
Yeah, that looks right.
Okay, so sodium, hydrogen, carbon, and oxygen are the different components in baking soda. What about baking powder? What's the chemical formula for, or what's the chemical formula for baking powder?
Sodium hydrogen carbonate. According to Byju's, sodium hydrogen carbonate is the chemical term for the baking powder. You might see it in the supermarket called soda bicarbonate.
Okay, so this is a tough one here because, like anything on internet here, there are different little sites that kind of talk about baking soda and baking powder. And it's not going to be on any exams or anything like that, but it is a very interesting thing in terms of cooking, right? Baking powder is not just this chemical formula here. This is the chemical formula for what we call baking soda. And when you buy baking soda, this is what you're getting, a pure compound with this chemical formula. Baking powder, on the other hand, if we go to Wikipedia in here and see what it says here, it's a dry chemical leavening agent, a mixture of the carbonate, the bicarbonate, and a weak acid. So there are a handful of things in here. This contains particular type of baking soda contains monocalcium phosphate, that's the weak acid, sodium bicarbonate, and cornstarch, that's the non-sticking agent, right? So even other compounds found in baking powder. So baking powder is an example of a mixture. All right, good. Each of the following changes is either chemical or physical, and we want to classify them. The condensation of steam. How about this? What does that mean, condensation of steam?
Steam, like condensing.
That's right. So if I have steam, what that is water vapor floating around, water molecules that are warm enough that they don't stick to their neighbors, so they float around separate from each other in the air, but they condense into a condensation, means they are combining into one body of liquid, and that forms water in the liquid phase. All right. Steam isn't really a gas; it's condensed, or it's moisture in the air. It's liquid that's in the air, like clouds. Gas is when the water molecules don't stick together at all, and they just completely separate, right? And they form a gas phase, right? So condensation of steam from either water floating around in the air or a gas to a liquid, that's just a physical change, right? The chemical formula hasn't changed at all. How about the burning of gasoline?
Anything that's burning, that's chemical change, right?
That's right. Now, I can't remember. I think I said that this was a physical change, but that's correct. Condensation of steam is a physical change, but burning of gasoline, that's a chemical change. All right, souring of milk. All right, burning of gasoline. Let's talk a little bit about that just because it's interesting. C8H18, that's our little representation of gasoline. It's called octane. It's the average compound that you find in gasoline, the most abundant maybe. We combine it with oxygen. That's the process of burning. Burning is when you combine something with oxygen. The products here are carbon dioxide and water. And that's always the products of combustion. Combustion is a fancy word for the combination of a hydrocarbon, something that just contains carbon and hydrogen, and oxygen. All right, so we call this combustion. We're going to refer to that throughout the semester, and throughout chemistry you hear about combustion all the time. And it's a chemical reaction. All right, the souring of milk. What do you think?
That's got to be chemical, right? Because you're changing it completely.
That's right. It's changing from milk to, we're breaking up part of the sugars in the milk and creating different acids, right? Okay. Dissolving of sugar in water. What do you think?
Combining sugar and water, does that change the chemical formula?
It doesn't, does it? If I just take water, H2O, and sugar, my favorite form of sugar, C6H12O6, that's glucose, right? The biochemical, uh, main biochemical sugar, all right? Glucose and water. If I combine them together into a container, the glucose will dissolve in the water, but it won't react. There's no chemical change, all right? It just goes from chemical or glucose solid to C6H12O6. We put an AQ there to mean it's dissolved in water. Okay, melting of gold.
Melting is just a physical change.
Very good. Melting of gold is just a physical change. Excellent. All right, number 28 here. How about coal burning?
Coal burning, we said burning, that's an example of combining something with oxygen, right?
That's right. It's called combustion, and it's very similar to what we drew. Where did we write it? Right here, right? Combustion. Instead of C8H18, it's going to have different numbers here. 8 and 18 are going to be different, but it's still the same process. Okay, ice melting.
Melting is just solid to liquid, that's physical change.
Good. We're not changing the chemical formula. Mixing chocolate syrup with milk.
I don't know, is that a reaction?
It's not a reaction, but you might not know for sure whether there's a reaction or not. But generally, if there's no heat that's produced, if there's no bubbling or change in color, then there's likely no chemical change that's occurring. So yeah, that's an example of a physical change. Or not even a physical change. We're just creating a mixture, right? All right. How about the explosion of a firework?
It's got to be chemical. I don't know what the reaction is.
Well, it's something. It's a hydrocarbon again. It's not C8H18, but it's got some chemicals in it. Similar, lots of carbon, lots of hydrogen, probably some nitrogen and some other metals, because fireworks often want to have metals which give you color, right? So, but very similar process here. So that is going to be a chemical change. Okay, good stuff. Number 38 here, give the name and the symbol of prefixes used when SI units to indicate multiplication of the following exact quantities. All right, so if we want to say 10 to the third, what's another way of using 10 to the third, saying 10 to the third with one of our prefixes out there? So for those of you who are still kind of trying to figure out or remind yourself about scientific notation, then we say 10 to the third is also 10 times 10 times 10. So that's 1, 1, 2, 3, like that. It's 1,000, right? 1 times 10 to the third. You take the decimal place on 1, and you move it over 1, 2, 3 times. Okay? So 1,000, what's one way to say 1,000 instead of just 10 to the third?
I can't remember the prefixes.
Well, let's get them out. Okay, chemistry prefixes. Let's see if that gives it to us.
Here are some pictures that match.
So here we have some prefixes. All right, 10 to the third. There it is. 10 to the third is kilo. Kilo. All right. So kilo means 1,000. So this is 1 times 10 to the third is 1 kilo. All right. Let's write that down. Let's look at some other ones here. Because see, we have 10 to the third kilo. We have 10 to the sixth, which is a mega. So 1 kilo, let's use grams because it's comfortable to have something there, is equal to 1,000 grams. All right? Yeah, there we go. All right, 10 to the minus 2, 1 times 10 to the minus 2, 1 times 10 to the minus 2 is just moving the decimal place over to the left twice, or 0.01, and if we want to call it grams, right? What's the way that we can express that in grams? There, with the prefix, instead of saying 0.01 grams, we can use a prefix. We can bring our prefixes back up here. All right. Here's 10 to the minus 2. Centigram. Okay. So, we're used to hearing terms like centimeter, but 1 centigram is 1 times 10 to the minus 2 grams, or 0.01 grams. Okay. I could also have done like this. Let's use liters for a second here. 0.01 liters. That's 1 centiliter. Now, if I wanted to use not just my prefix centa, but we don't really use centa much as a prefix for things, right? We just skip right to milli. So if I wanted to express this in terms of milliliters, for example, well, then I would need to move the decimal place over 3 times, 1, 2, 3, and that would equal 10 milliliters. So if I had 0.01 liters, I could express it as 1 centiliter, but usually what you'd hear is 10 milliliters, because milliliters is a unit that we use in the lab. We don't use centiliters at all. Okay, so 0.1, that's 10 to the minus 1. 0.1, I can express that with centa. I can express it with milli, right? How many, let's put some units on here so it feels more comfortable. Let's say if I have 0.1 liters, how many milliliters is that, Fred?
Milli, you move 3.
That's right, you move 3.
So 0.0001?
No, you don't move 3 this way, right? Because 1 milliliter is 1,000th of a liter. Here I have 0.1 liters, and 1 milliliter is 1,000th. That's 100th. So that's 100 milliliters. Okay? So 100 or 1,000 milliliters, that's equal to 1 liter. So I could write 1 liter is 1,000 milliliters, and 0.1 liters, this moves place over 1, this has to move over 1 too, would be 100 milliliters. Okay? So a milliliter is 1,000th of a liter. And if I only have 1/10 of a liter, then I only have 1/10 of my 1,000, which is 100. All right, 10 to the minus 3, 0.001, right? So I've taken the 1 times 10 to the 3 and moved the decimal place over. Oops, sorry, negative 3. Yeah, negative 3. 1, 2, 3. So 1, 2, right? So 1 times 10 to the minus 3 is equal to 0.001. All right. And I can express this if I have, let's use liters again, 0.001. Well, let's use grams. 1.001 grams. All right. How many milligrams is that? Milli is 3 decimal points.
It'd be 1.
Very good. 1 milligram. Okay, you getting the hang of it? So let's try that again. 0.001 grams. This time I'm going to express it in centigrams.
Why?
Well, yeah, good question. Why? We already got it in milligrams, but just for a little bit of practice, centigrams is 2 decimal places over. So this is 1 milligram. This is only going to go 1, 2 over. It's going to be 0.1 centigrams. Okay, good stuff. Number 39. Oh, no, we're not quite done here. Good. A couple more on 38. 1 million. All right, so we have 1 million. 1, 2, 3. 1, 2, 3. How many is a million? Or how many, what is that in scientific notation? Can you write that in scientific notation, Fred?
Yeah, I can do that.
1 times 10 to the what?
Let's see. 1, 2, 3, 6.
That's right. So you counted 1, 2, 3, 4, 5, 6. So 1 times 10 to the 6th is equal to 1 million. All right, good stuff. Now, how can I express 1 million? Let's use a unit like grams. That's equal to 1 times 10 to the 6 grams. Now, how can I express that in with a prefix?
You have that chart?
Yeah, we have to know these little prefixes, don't we? So looking at our chart here, if I want to go 10 to the 6th, I can see that that's M, capital M for mega, mega. So 10 to the, or 1 million grams is the same as 1 megagram. Now, we don't use mega very much. We don't use giga. We don't use tera. That's these other ones up here, right? We use kilo a lot, but we don't use anything really that's much bigger than that in chemistry. All my life, you never really see that. Maybe in physics a little bit. But you do hear it and use it all the time. Where? Do you know? Do these look familiar?
Files?
Yeah, computer files. That's right. File sizes, right? Megabytes, gigabytes, terabytes. You hear that all the time. And that's roughly the same reference to these values. Okay. So where did our, there it is. Okay. This one here. What's that one in scientific notation, Fred? Can you write that in scientific notation? And if you folks at home aren't confident in scientific notation, go ahead and write it down really quickly before Fred tells you. Push pause maybe. Okay, tell us, Fred. What is it? Push pause if you haven't done it yourself yet at home.
1 times 10 to the minus 6.
Is that right? Did you count them right? 1, 2, 3, 4, 5, 6. Very good. 1 times 10 to the minus 6. All right. Oops, where am I writing that? There it is. Okay, 1 times 10 to the minus 6. So, Fred, 1 times 10 to the minus 6. Do you remember the prefix for that one?
I think I do.
Or how do you remember?
Well, it goes like 3, 6, 12, 3, 6, 9, 12, right?
Okay, so you're referring to like it goes 1 times 10 to the minus 3, 1 times 10 to the minus 6, 1 times 10 to the minus 9, 1 times 10 to the minus 12. There's prefixes for these. Do you remember the 1 times 10 to the minus 3?
That's milli.
Very good. Milli. And I always remember 9 because that's nano, 9 nano, right? And then that's the way it helps me remember that micro is in the middle there. Micro. So 1 times 10 to the minus 6 is a micrometer, right?
That's right.
Or micro, whatever it is. So 1 meter has 1 times 10 to the 6th micrometers. Or 1 times 10 to the minus 6 meters, that's, whoops, let's do it on top, is the same as 1 micrometer. Now notice how I make that micro sign, right? It looks something like that. That's the Greek letter mu. Okay? Excellent. Number 39. Give the names and prefixes of the quantities indicated by the following symbols using the SI units. So, C.
That's centa.
That's right. That's not used a ton except for with centimeters. We don't want to talk about centiliters ever, but centimeters are important. So I want to know how many centimeters are in a meter.
Centas, that's 100.
Very good. 100 centimeters per meter. Now, it's not always just that easy to answer, right? Sometimes you have to think a little bit. Like, for example, if I say I have 200 centimeters, how many meters is that?
2 meters.
Okay, good. 2 meters. If I have 0.1 centimeters, how many meters is that?
Is that 10 meters?
10 meters?
Oh, no, that can't be right.
Right. 10 meters would be way too big, right?
So you have to move the decimal place over twice?
You have to move it over twice. 1, 2, like that. So it's 0.001 meters. That's 12.1 centimeters. Okay, those are 3 conversion factors there. All right, D.
That's deci.
Very good. Deci. 1/10 G.
Well, that's like a gigabyte. That's 1 times 10 to the ninth.
Very good. Gigabyte. Okay.
Oh, that's kilo. We've been talking about that one.
Very good. Is that, what is it?
10 to the third, right?
Yes, 10 to the third. Kilo. Good. M.
That's like a millimeter.
All right. How many millimeters are there in a meter? 1 meter. How many millimeters?
It's not 100. It's 10 times. It's 1,000, right?
Very good. And we just talked about how this is our milli, micro, and nano, our prefixes there. We didn't fill that one in pico, right? All right. So N.
That's nano, 10 to the minus 9.
Very good.
That's pico, 10 to the minus 12.
All right.
That's a terabyte.
Terabyte. What's a terabyte?
Let's see. It goes kilo, giga, kilo, mega, giga, tera. So does that mean 10 to the minus? I can't remember.
So we have our 10 to the minus 3, minus 6, minus 9 here. But 1 times 10 to the third, 1 times 10 to the 6th, 1 times 10 to the 9th, 1 times 10 to the 12th. This is our kilo, mega, giga, and tera. So tera is 1 times 10 to the 12th. Okay, good stuff.
Am I going to have to memorize that?
You know, when you memorize something, it goes into a portion of your brain that kind of easily gets forgotten. You're going to want to look these things up when you need them, and you won't ever need them on an exam or anything, except for milli and centa, right? Centimeter, 1 times 10 to the minus 2. But I think that you already have those memorized from schools a long time ago, centa and milli. And then kilo also, a kilometer, kilometer, that's one that you should know. So those three are the ones that you really need to know.
Okay.
You ready, Fred?
I'm ready.
A large piece of jewelry has the mass of that, and we have a graduated cylinder. Do you know what a graduated cylinder is, Fred?
Not really. It got its degree.
It graduated. It got its degree. That's right. The word graduated means marked. So when you graduate, we have a mark to know how much schooling or how much experience you have, right? So a graduated cylinder is a cylinder. It often has a base to keep it from spilling. And you fill it with liquid, right? So it can measure out those liquids. It has graduates or marks on the side that indicate how much volume there is up to that point. So what we do here is we fill it up to a certain volume, 48.6 milliliters, and we put in our mass of our block. Here it is. It's just a piece of whatever. I throw it into here, and it has a mass of 132.6 grams, and its volume can be identified by seeing how much the volume of the water goes up. So the new volume of the water is what, Fred? Can you read that and figure it out?
It says the volume increases to 61.2.
Very good. 61.2 milliliters. So the difference between those two is the volume of this thing. It displaced the water when it sunk down in it, right? If it sinks down into the water, it displaces that water. So the volume difference there can be identified with a calculator, right? So I go 61.2 minus 48.6, and that tells me that it's 12.6 milliliters. That's the volume of my piece of material, okay? And now we want to know the density of this piece of jewelry, right? This is some sort of jewelry. Sorry, I just drew it as a block, but it could be, you know, a very precious gem for whatever reason. So what's the density? Do you remember what density means is?
I can't say that I remember very well.
Density refers to the relationship between the mass of something and its volume. Okay? So the mass over the volume, that is the density. So if I have this piece of jewelry and I say its mass is 132.6 grams, that's what they gave us, I can put that over the volume, which we got from taking the difference there, 12.6 milliliters, and the density will be 132.6 divided by 12.6. It will be 10.4 5. I have three significant figures. Let's see, did I do that right? 12.6. That's three significant figures. I have three significant figures to deal with here, so 10.5. And the units now have to be maintained, units of grams per milliliter. So that is the density of the piece of jewelry. So if we assume that the jewelry is made of only one substance, what is this substance likely to be? Well, we can try to look it up, right? We can try to look and find out substance that has a density of 10.6 or 10. What is it? Yeah, 10.52 grams per milliliter. Substance with a density of 10.5 grams per milliliter.
According to chiasty.net, the density of silver is 10.5 grams per cc. Find the mass of Ag that occupies 965 cc of space. 3. Under certain conditions, oxygen gas has a density of 0.0034
All right, stop. So it says, I mean, it's silver, right? It looks like it's silver. Now, it might be something else. There are other materials that might have the exact same density, but it looks like this is silver. Now, notice the units that they give here are grams per cubic centimeter, and they kept saying cc. And that's an important thing if you're going into the medical field to recognize that cc means cubic centimeters. And for water, cubic centimeter of water, 1 cubic centimeter of water is equal to 1 milliliter of water. All right? So a cubic centimeter is the definition of a milliliter of the material. Okay, so this is my centimeter by centimeter by centimeter here, right? Cubic centimeter. It's 1 milliliter. Okay, number 40. Good job. The following numbers in scientific notation.
I'm good at this now.
You're good at this already? Excellent. Well, let's zip right through these, right? 711, how do you express that in scientific notation?
You want to express a number between 1 and 10.
That's right. So 711, you find the number that can be between 1 and 10 by moving that decimal place over. So 711.0. Moving the decimal place over twice will give me 7.110, right? Maintain all the significant figures. Then what?
Then you use times 10 to the.
Times 10 to the what?
Well, you had to move the decimal place over, well, let's see, -2 or +2?
So what you want to do is find out how to convert your new number to the original number, right? So I want to know how to go from here to there. And I would need to move this to the right, right, to get to that point. So that's a +2. So 7.110 times 10 to the 2 will equal 711.
Okay, so the next one is 2.39 times 10 to the -1.
Okay, good job. 2.39 times 10 to the -1, he says, and that's 0.239, okay? And I'm moving the decimal place over once to the right to go this way. If I go from 2.39 back up to there, I have to move it over to the -1. I have to move it 1 to this direction, right? So that's -1. Excellent.
That's easy. I got it now. 9.0743.
Oh, you're on to the next one? 9.0743
times 10 to the 5th.
Times 10 to the 5th?
Or 4th.
4th, right? 1, 2, 3, 4 is what would be necessary to go to 90743. 1, 2, 3, 4.
And then 1.342 times 10 to the 2?
10 to the -2, right?
Oh, yeah, -2.
So 1.342 times 10 to the...
No, 2.
Oh, yeah, you're right. Times 10 to the 2. Times 10 to the squared, that would, times 10 squared would give us 134.2. Okay, very good. There's some more in there, right? How about this one here?
5.499 times 10 to the what? Minus 2?
Good. 5.499 times 10 to the minus 2. If we wrote that out the way standard form, 0.0012, right? 5499. So I move this over 1, 2, negative 2, and I get that value.
1 times 10 to the minus, or, well, 1.00000 times 10 to the minus 4.
All right, good. So to maintain all of those significant figures, 1, 2, 3, 4.0. Did I overdo it? 1, 2, 3, 4, 5. 1, 2, 3. That's right. So I have 6 significant figures here. And to express that in scientific notation, I have to make sure I maintain all of them. 1, 2, 3, 4, 5, 6 significant figures times 10 to the 1, 2, 3, 4, positive 4 to go from here to there.
7.3859.
7.3859 what?
2.
7.38592 times 10 to the what?
Oh, that's, well, that's a lot of numbers.
Yeah, so maybe I write it down. 0.1234567388592. All right. Can you imagine trying to tell somebody this value? Say, my number is 0.0000007388592. It's not a number that's going to be easily retained by somebody listening. It'll be a little bit easier if you say 7.38592 times 10 to the. Is this going to be a positive or a negative number?
It'll be a negative number.
How many do I have to go?
7.
Is that right? 1, 2, 3, 4, 5, 6, 7. You're right, negative 7. Let's make sure I counted that right here. So it's going to go from here. 1, 2, 3, 4, 5, 6, 7. Okay, good. All right. Okay, so number 45 here, express the following numbers in exponential notation. That's essentially the same thing as scientific notation. So here we go, 45, 704. How do you do it?
7 times 10 to the, 7.04 times 10 to the 2.
Very good. 7.04 times 10 to the 2. How about the next one?
3.344
3.344, what?
times 10 to the minus 3.
I think you just move it over twice, right?
Oh yeah, 10 to the minus 2.
Okay. These, I think, are getting a little bit easier for us, don't you think?
Yeah. 5.479 times 10 to the 2.
Very good.
2.2086 times 10 to the 4.
Very good.
1.00000 times 10 to the 3.
Good.
Oh my goodness, what is that?
Let's count those zeros there for us. 1, 2, 3, 4, 5, 6, 7, and then 8.
Okay, so 6.51 times 10 to the minus 8.
Very good.
7.157 times 10 to the minus 3.
Excellent. Good job. Significant figures in problem number 48, right? How many significant figures are contained in these measurements? How do you feel about significant figures?
I don't like them.
Why not?
I don't get them.
Well, the thing to remember about significant figures is that we make sure we recognize that in chemistry, numbers are not just like in math, some beautiful artistic value that we can do all sorts of manipulations with. They're always, in chemistry, they're always measurements. They're always measurements of some kind. And when you make a measurement, the accuracy or the precision of your measurement depends on the tool itself, right? So we need to express to each other the uncertainty that's in that measurement by using significant figures. Okay? So if I make a measurement on a scale and it says 38.7, I'm not going to write 38.7000 because I want to write more values. The 38.7 indicates that those are the significant figures that have been given. Okay? And in scientific notation, we want to make sure that when we write things in scientific notation, we maintain those significant figures. So for example, 38.7 in scientific notation again, I have three significant figures in 38.7, 3.87 times 10 to the 1, right? That would be our scientific notation, grams. Those are our units. I wouldn't want to write 3.870 times 10 to the 1 grams because now that is showing 4 significant digits. Okay? So the answer here is 3 significant digits for A. How about this one?
Is that, well, I don't know.
Well, there's only one value, right? So there just has to be one significant digit.
Okay.
So how about here?
Now, is that 5 or 7?
That's good. We know that there's 1, 2, 3, 4, and 5, because every number is definitely going to be a significant digit. But the zeros in between are placeholders. So there was material, this is kilograms, so there was mass up to this amount, and there was mass down to here. So if there could have been some mass here, then we would have recorded it. So those are significant figures. So the answer is 4, 5, 6, 7. All 7 values are significant. How about here?
Is that last zero significant?
Yes, it is, right? It's showing, we put it in there to make sure we're showing people that it's significant.
So that's 6?
That's right. 1, 2, 3, 4, 5, 6.
Are those zeros significant?
Those zeros aren't significant because we're measuring centimeters cubed, which is the volume of something, right? And we didn't have anything here, and we didn't have anything here, right? We just had these values here. So if we had something, we could fill it in, but we didn't. So there's only those 3 significant digits.
Okay. Is that zero significant?
That zero is significant. That zero is the estimate, or the scale gave us that last zero, right? And so we wrote it down. So there's 3 significant digits there.
How about that one?
What do you think?
The zeros before I don't think are significant, but the zeros after I guess are, huh?
That's right, they are. By writing those down, the person was expressing that they had the ability to measure those spots, but there was nothing there. So that's 4 significant digits. All right, number 49.
Okay, that's 2.
Very good.
And that's 3.
Very good.
Oh, that's easy too. That's 5.
Very good, because the zeros are surrounded by numbers.
And I guess that one's not too bad either, right?
That's right, that one's not too bad either because it's got a 0 at the end, and we already identified those as significant, so that's 4, right?
Yeah. Well, that's 6.
Good.
That's 2. Now that one is 5.
That's right, good. Excellent. Good work. What number are we on?
Number 50.
All right, number 50. The following quantities were reported on the labels of products. Determine the number of significant figures.
Oh, that's just the same thing then, right?
That's right.
2, A is 2, B is 2, C, is that more than 1?
Nope, C is just 1. Very good.
2, 3, 3, what's G?
That is just 1, right? 1 significant figure.
Okay, and then 3 or 4?
That's 4. That 0 again is there because somebody is trying to express significant figures.
Okay.
Number 51. So rounding each of these to 2 significant figures.
43.6 goes to 0.44.
That's right. 0.436 goes to 0.44.
9.0.
Very good.
27.0.
No, not the 0.0, just the 27.
Okay, just the 27. 135. Now, what does that do?
We can just round it up, all right? When there's a 5 there, let's just round it up. There are some people who have the philosophy of rounding down when it's odd or even or whatever, and that's fine. And if you're excited about doing that, or the lab is excited, the lab will tell you, okay? But in general, you can get away with just rounding up when you get to a 5 there, okay?
All right, so 136, or no?
Just 140, right?
Oh, yeah, 140. All right, 1.5.
Very good.
4.5.
Good. Excellent. Nice work. All right, so we had an archery contest, huh?
Guess that's what it looks like.
And we had we want to figure out who the winner is, I guess.
No, we just want to know which one is more precise and accurate and that sort of thing.
Okay. All right. So, which archer is most precise?
Does precise mean in the middle or because it's either W or X?
All right. So, precise, I remember, sounds like pretty. And it's pretty when it's all clustered. It looks sloppy when it's all over the place, like Y and Z, right? Those are sloppy. But X is nice and pretty. It's all precise in one location.
Okay, so X is most precise.
That's right. But which is more accurate? That's the one that has it right in the middle, right? And so W is more accurate here because it's closer to the middle. All right? Which is both least precise and least accurate?
Is it Y or Z?
I don't know. Probably Y because Z got some on the target. Y got nothing on the target.
Okay.
So it's least precise. Now accuracy here would probably be measured by the average location. I don't know what you say the average location here would probably be right about here. What do you think?
Well, maybe.
The average location here would probably be a little bit closer, maybe over here. I don't know. So each one of these is more accurate would be hard to say. But if you're not very precise in your measurement, your accuracy really doesn't matter too much. So, okay, 56. Classify the following set of measurements as accurate, precise, both, or neither. All right, so we're trying to weigh chocolate chip cookies, and we found these masses. What do you think?
They're all about 15 grams and...
All right. So notice that the first significant figure is the only one that's the same. And really, if you were to round up, it's different for the first, this different for the second one than the first, third, and the fourth, right? So there's no accuracy there, right? And there's no precision either. Does that make sense?
How could you tell?
Because none of the digits here are the same throughout, right? This one would round up to 2. This one would round up to stay at 1. This would be 2. This would be 2. The 7, the 3, the 9, and the 6, they aren't the same. The 2, the 0, the 4, the 9, none of these values are the same. So these are all relatively far from each other. It might have the accurate weight of whatever chocolate chip cookie you're looking for in terms of the average. But again, if the values aren't very precise, then it doesn't really matter much. How about this one? The volume of a batch of pipettes. All right.
Well, that's pretty, I don't know, pretty accurate and precise.
Yeah, all of these would be 2.7, 2.7, 2.7, 2.7. So yeah, that's pretty accurate and precise. Some people might want it a little bit more precise on the bottom there, like this. Look at this, determining the purity of gold. Definitely accurate and precise. But it always really depends on the laboratory's concern about how accurate or precise you want to be. Generally, a rule of thumb is if it's less than 5%, and the way you can determine the percent difference between two values, right? So let's look at, for example, 17.2 and 13.05. 13.05, this is from the checking the consistency of the cookies. Whoops, 13.05 and 17.27. What's the difference between those two? Maybe my correct value is supposed to be, let's do this instead. Let's identify a correct value of 16. That's how much we want our cookies to weigh. Our factory is making cookies, and these are some examples of 2 cookies that were made. We want to see how far off our setup is, our cookies are how far away our cookies are from being accurate. So we go 16 minus the 13.05. All right, 2.95 is our difference. And then we divide that by our 16 and then times that by 100. So we took our difference divided by what we were after, times it by 100 to get it into percentage. So this one is off by 18.4%. All right, we do the 17.27 minus the 16. That's 1.27. Divide by the 16 now. That's 7.9%. of our actual value that we're after. So both of these are more than 5% off from, let's say, some value of 16. They would also be likely more than 5% off from an average that you would get from looking at those four. Okay, very good stuff.